Hello, my dear students. Now we will discuss about the convergence of properties of Fourier series. So, in this lecture, we will learn about the convergence Fourier series and how that in which condition it converge. Converge means if uh, if there is an equation like this, in what condition it will converge. Converge means it will have a limit. Okay. Uh, for your example, kind example, that is a circle, that is the point. So convergence means if you know the circle, the equation of the circle, you can draw the circle. But if you want to converge it, you have to make the circle to the point. That means radius should have to be 0. That means it should have to be tends to 0. Then it will converge in that point. So the main part of the Fourier series is this equation, that is the governing equation of Fourier series, where the ck is the coefficient, and as you know, if you take there is a here the section k is infinite, minus infinity plus infinity. Let xn denote the Fourier series truncated after nth harmonic components given by x and t. If it is nth harmonic, so the infinity will be converted to n, as you can see here. And here we are interested in whether limit n tends to infinity x n t is equal to xt. Right? When the limit n tends to infinity, so it will equal to xt. After that, the point came that you have to find out the error. So when you have to find the error, so that is the general equation formula, the formula with the infinity formula, and if you have the nth term formula, so if you just subtract these two formulas, you will get the error out of it. And if you want to find out the MSE, that means mean squared error, that means this kind of error is quite precise to find out. So we find out the mean square error. The mean square error here is en 1 by t integration of t ent whole square dt. If limit n tends to infinity, ent is equal to 0 for all t. That means if n tends to 0, that means the error goes to 0 at every point. The Fourier series is said to converge pointwise to xt. That means if the n point tends to infinity, so the error will be very much less. That means it tends to 0. And if convergence is pointwise, that the rate of convergence is the same everywhere, the convergence is said to be uniform. If you want to have a uniform convergence, that means convergence is pointwise, the rate of convergence is the same everywhere. The rate of convergence is the same everywhere. So that is the part. Now, if limit n tends to infinity and en is equal to 0, it means when you find out the mean squared error, the MSE, and it tends to 0, you will find the energy error goes to 0. The Fourier series said to converge x in the MSE sense. That means in this MSE sense, if en is tends to 0, in n tends to infinity, the en tends to 0. If it happens, so that will known as the x, the input will be converged in MSE sense. And in previous thing, we will know that will be known as the pointwise sense, that is converging. And that is the pointwise convergence implies MSE convergence. But the convergence converge is not true. Thus, pointwise convergence is a much stronger condition than MSE convergence. In MSE convergence, that means there will be no energy will be lost or anything. That is quite a pointless thing. But the main thing is that the pointwise convergence is the more appropriate or approved sense of convergence. Now, in the next slide, we will know that how that will be converge a Fourier series in continuous case. If a periodic signal x is continuous and its Fourier series coefficient ck are absolutely summable, that means it should have to be less than infinity, absolutely summable, then the Fourier series representation x converges uniformly, pointwise at the same rate everywhere. How that can become? That means how that will be converged? That is a periodic signal, that is sinusoidal signal that you have seen here. That is the sinusoidal signal. In that sense, in the sinusoidal signal, if you want to draw this really correctly, that is the line. This is line. Now we are drawing the sinusoidal signal here. That is the sinusoidal signal. Here you can see that is the periodic signal, and if it's continuous, and that's not the discrete signal, as it represents the t, and that represents the xt. So that is a continuous signal, and that has an coefficient of ck, absolutely summable. So this kind of Fourier series representation, x will converges uniformly, that will converge uniformly in pointwise direction, because the period of time is period of time is capital T is 0 to twice pi, so it will converge at any time. When it converges, it will make a circle of 360 degree, so it will converge uniformly. Since in practice we often encounter signals with discontinuities, a square wave, the above result is of somewhat limited value. That means if that is a square wave, then what will happen? In a square wave, we will think that in that part it will not uniformly converge, because the signal is not a periodic as in previous signals. So that is the part of the convergence. So let us discuss about the finite energy case. In previous case we will discuss about the continuous case. Now we will discuss about the finite energy case. In finite energy case, just like MAC sense, that means mean square energy convergence. So in that case, if periodic signal X has finite energy in a single period, if it is a finite energy, it will have infinite power, that kind of thing. If it has an infinite power in power signal, it will get a limited energy. So the Fourier series convergence in the MAC sense in single period, that is the condition of that. It should have to be less than the infinity. Since the situation of practice interest, the finite energy condition in the above theorem is typically satisfied. The theorem is usually applicable. It is important to note, however, that MAC convergence, that is E is equal to 0, does not necessarily imply pointwise convergence. The main thing is that in MAC convergence we predict energy to be 0, but the thing is that energy can't be 0. So that is the part that we can't take. That is theoretical part, but it's the practical part. The above convergence theorem does not provide much useful information regarding the value of x bar t at specific values of t. Okay. Consequently, the above theorem is typically most useful for simply determining the Fourier series converges. Now, the convergence of Fourier series in Dirichlet case, that is the important part of the Dirichlet conditions. What are the known? What we will know about the Dirichlet condition? What is Dirichlet condition? The condition of the periodic signal x are as follows. Over a single period, x is absolutely integrable. That means that is the case less than infinity. Over a single period, x has a finite number of maxima and minima. X is bounded variation. Over any finite interval, x has finite number of discontinuities, each of which is finite. If a periodic signal x satisfies the Dirichlet condition, then the Fourier series converges pointwise everywhere to x, except at the point of discontinuity of x. Each point t is equal to ta of discontinuity of x. The Fourier series x bar converges to this. That is the even, and that is the odd. That is the odd and that is the even, minus and plus, that has been here, but this denotes value of signal x on the left and the right hand sides. That means that is the left hand sides and that is the right hand sides, okay, to discontinuity respectively. That is the condition of Dirichlet condition. Okay, you have to find it out to make it a bounded variation. Dirichlet means to make thing bounded. Since most signals tend to satisfy the Dirichlet conditions and above convergence result specifies the value of Fourier series at every point, this is often very useful in practice.